Hey guys, so sorry about this. I'm a bit of a chronic insomniac. And also a few of you indicated that you wouldn't be able to make this meeting, which is Friday the 21st of March, 25. So I figured I would just kind of record this and then maybe you guys can watch asynchronously or just whatever on your own time. Of course, you're free to ask me questions or whatever. Yeah, I guess I'll just get into the worksheet for now. If you're ever stuck at any time, yeah, just like pause. I won't be really like giving time to like solve the problems because I mean it's just a video, I guess. All right, so the first part, what is the real part of z1 plus z2? What we're gonna do for this is first recognize that the real components and imaginary components of complex numbers are always going to be like orthogonal. They're never going to like interact with each other, right? So if we want to take the real part of z1 plus z2, we can do real of z1 plus real of z2, and that's just going to equal 5. Okay, for the second part, what is the imaginary part? Yeah, so same logic. We can do the same thing actually. We have imaginary of z1 plus imaginary of z2, and that's just going to be equal to 1j. Again, we use j not I here because we don't want to mix it up with current, right? All right, part C, how do we visualize the polar representation of complex numbers z equals ae to the j theta in the complex plane? Okay, so for this problem, what they want us to do is take a complex number plane like this. Say this is the real component, this is the complex component. Oop, no, imaginary rather. The whole thing is complex, right? And the magnitude is always just going to be equal to a. So whatever this is going to be with magnitude, let's call it vector v, is going to be equal to a. Oh, that z actually, they give us z. And we also know that this angle is equal to theta. Yeah, that's just like how we visualize this kind of thing. That's just what this complex number z equals ae to the j theta means. It's just an easier way to see it. Okay, so applying this knowledge, part D, for the vector it gives, which is 7e to the j 30 degrees, what is the magnitude of that vector? And yeah, I mean, it just tells us the magnitude is going to be equal to 7. And part E, same thing, kind of. It asks us for the angle from which, for which we can just pull the angle from the exponent of the E by definition of how we represent these numbers. That's just going to be equal to 30 degrees. Part F, given z equals 5e to the j 90 degrees, so a different z vector, what is the real part of z? Ooh. And this one's pretty interesting, actually. So what we can do for this problem is we can draw this vector on the complex number line first. So we know that the magnitude is 5, and we know that the angle is 90, right? So if we draw that vector, again, that's this one right here, 5e to the j 90 degrees. We're working on part F. We're going to see that the vector looks like this, right? It's just straight up. We know the magnitude is 5, and we know that this is 90 degrees. Just visually, we can tell that this vector is entirely imaginary. And what that means is that the real component is going to be equal to 0. So this is basically just equal to 5j. Yeah, and I say basically, but that's exactly what it's equal to. This vector, another way of writing it, is just 5j, and we can see that from our complex representation. Now for part G, what is the imaginary part of z? Well, in the last part, I guess I kind of answered my own question there, but what we can tell from the complex representation of the number is that, again, since it is entirely imaginary, we can deduce that all of it is imaginary, so all 5 of its magnitude is going to be imaginary, so the answer is 5 here. Okay, time for this stuff. This starts a new section of the course which is going to be not just normal AC analysis like we've seen in past weeks, which included, for example, like time varying, like RC circuits, where if we plot, for example, voltage across a capacitor as a function of time, in some RC circuit, we would see some level of asymptotic behavior. You know, this is kind of a gross thing, right? And so, we don't want to work with time varying signals, is the idea of this section of the course. And rather, what we like dealing with is complex numbers. And it's actually possible to reduce all of our like sinusoids, especially, well, that's what's focused on here, into complex numbers so that we don't have to work with time varying sinusoids. And yeah, again, rather we just work with imaginary numbers. So how we get started here, we're gonna start by kind of deriving everything from the ground up. So what that starts with is this thing, Euler's identity. So let's start this problem. Euler's identity, this is just the statement of it. E to the j theta is equal to cosine of theta plus j times sine of theta. Okay. And the proof of this was maybe covered in lecture, I'm not too sure, but yeah, if you Google this thing online, it really shouldn't be too much of a problem to find a proof. The second part's gonna be check that cosine of theta equals this expression, and then in order to do that, all we need is Euler's identity. Again, by the way, if you need to pause at any point, I mean, I don't blame you. Please do, honestly. But yeah, let's just go ahead and get started. Cosine theta, well, first off, we start with the last identity. So I'll just go ahead and copy that here. And now let's copy something else. So our hint from the problem is that we're looking for something in this form. And how can we get that? Well, what we can do is we can rewrite this expression, but instead of theta, let's use negative theta. So again, this is just Euler's identity, right? And what we can see actually is that since cosine is a even function, we can get rid of this negative because that means that cosine of theta is going to be equal to cosine of negative theta, right? We can rearrange some exponents here. Negative j theta, and that's this is what we get. If we look at our two equations here, again, the left one is just the statement of Euler's identity, and the right one is the same thing, except we used negative theta instead of theta. If we add them together, we actually get e to the j theta plus e to the negative j theta. Another thing I have to mention here is that a trigonometric identity we can use here is sine of negative theta is equal to negative sine theta. So let's go ahead and replace that. Again, equivalent equations. So yeah, let's go back. So if we sum these two equations together, what we get is that this expression right here is going to be equal to 2 cosine theta. And in order to get the expression we're looking for in the problem, all we gotta do is divide both sides by 2. And then that's exactly what we're looking for. So what's the point of this? Again, we're deriving all the phasor stuff, meaning we're gonna find how we can use complex numbers to represent sinusoids. So this gives us a hint already. If we see cosine of theta, we already know that we can replace it with some complex numbers. And that's gonna make more sense later. Okay, the next problem, what is the phasor form of the signal? V of t equals V0 cosine of omega t plus phi sub v. From lecture, perhaps, we can just kind of write this equation down. How we're gonna define the phasor is going to be V, and we're gonna use the squiggly on top. It's just notation, right? It's gonna be equal to V0 times E to the j times 5e. I don't think they're having us really derive this thing. This is just sincerely just like a definition that they're having us use. And the idea is that eventually, once we get, this is a voltage phasor, right? We can compare it to like a current phasor or like something called the impedance phasor, which you can kind of think of as resistance, but we'll get to that. And then once we find these like relationships between complex numbers, then everything becomes simpler than you solving a bunch of differential equations were we to not use phasors and instead use a bunch of sinusoids. But we'll get to that. Part D, what is the magnitude and phase of the expression 8e to the j pi over 3? Okay, this feels kind of misplaced, but yeah, it's just like we did before. Magnitude is going to be 8. All right, magnitude. And then phase, that's just equal to the angle. We just use pi over 3 here. Oh, doing these problems, by the way, it's important. Be very careful whether they're giving you radians or degrees. Be really annoying to like mess up some of these like addition or subtractions because of like difference of like units, right? But yeah, we typically use radians in order. Well, actually, I don't know. Both are okay, but just make sure you're consistent, I guess. Okay, part E, transform the signal, this thing, to the phasor domain in the form AE to the JB pi. All right. So, again, what they want us to do is turn this thing into a phasor, like we did here. And so what we have to do is kind of, if we want to find the phasor of, let's say this is equal to V of t. Okay, and we're trying to find the phasor of V. That's essentially what we're being asked right now. So what would V0 be? V0 is like 12. That's like the amplitude, right? And then what we can do is turn cosine of omega t minus 3 pi over 4 into simply e to the j times minus 3 pi over 4. Yeah, so that's that. What is the impedance of a capacitor C? We're actually going to get into deriving this later in the worksheet, but we're given this for now, and that's just going to be equal to 1 over j omega c. So we see this word impedance, and it's natural to wonder, like, what does this mean, right? So for me, I believe good intuition for this is resistance, as we've seen in the past with DC circuits and like a non-phasor AC circuits, where it simply resists the flow of current, right? But when we look at something like this, like a capacitor, and we see 1 over j omega c, immediately we see this j in the denominator, and that tells us that this term is going to be imaginary, right? So, okay, like what is an imaginary impedance? And it's really hard to visualize, but something you can think about is when we see imaginary impedances, that's called the reactance component, actually. What that means is it's time varying. So it changes with as time passes. And that makes sense, right? If we think about an AC sinusoid and it's just going up and down all the time, if you think about like the resistance of a resistor, for example, which has only real resistance or also impedance, the amount of resistance does not change, right, as a function of the voltage. The amount of current changes, but the amount of resistance in the resistor does not change. Whereas when we look at a capacitor, the amount of like resistance to current flow is going to change depending on where in the sinusoid we are, if that makes sense. So that's why there's that imaginary component. And also we can tell that this kind of makes sense because if we look at omega, we know that a very small omega reaching 0 is kind of like DC, right? And what that tells us is that when omega is close to 0, then this impedance term is going to reach like the impedance of the circuit as it reaches like DC, right? So imagine a really small omega. what does this term turn into? 1 over j omega c. It's going to be very large, right? A very large impedance, if we think about just what impedance means, like impeding the flow of something, right? We know that at DC steady state, capacitors stop like the flow of charge completely, right? So we can kind of think of that as like an infinitely like large like stoppage or like impedance, right? So when we look at this term, if omega goes to 0, similar to DC, and then impedance, which we denote Z, is like really large. So Z like approaches infinity, right? And the same is true for if, well, not the same, but if omega approaches infinity, we're going to notice that this term becomes very small. I'll just write Z equals, meaning that Z is going to reach like 0. Because if we think about like a really fast changing sinusoid, yeah, the capacitor is not going to really have much effect. Okay, now let's move on to the inductor. We're also given this. The impedance of an inductor is J omega L. Again, we can perform our sanity checks with omega approaches 0 and infinity. We know that as like the flow of current doesn't change. Here's the governing equation for an inductor, by the way. So we can see that if the current is constantly changing, which happens when we have a very quickly oscillating circuit, then there's going to be a lot of voltage across the inductor, right? And the opposite is true if we have like a steady state voltage. So if we have a steady state circuit and there's no like omega like is approaching 0, then we're going to have that di over dt is going to be like a very small number, right? So therefore, yeah, the inductor is not going to do much. And then we can also see the same is true for j omega L. Okay, what is the impedance of a resistor R? That's just going to be equal to R. It doesn't really depend on omega. Yeah, that's just how that works, I guess. It's just like a resistance is like an internal property of some physical thing, and it's not gonna like, yeah, that's the idea. Okay, let's look at the impedance of a resistor R and a capacitor C in parallel. So why do we look at impedances here? Let's draw the circuit first. R and C in parallel. Well, I see there's some voltage. I don't know, who cares? Well, the magic in this actually comes from the fact that we can treat all like circuit components as we kind of treated resistors in the DC case. So if we do standard like our traditional voltage analysis with differential equations, it might get ugly, but we can kind of like, yeah, so I'll show you what I mean by treating everything like a resistor. So we see two things in parallel. There's going to be a resistor and a capacitor here in parallel, right? So what we can do is we can say, okay, the impedance is going to be equal to R, right? Let's say R and C here. R in parallel with C, which is going to be equal to 1 over R plus 1 over j omega C, which is also equal to 1 over R plus j omega C, which is, well, we like to simplify to R over 1 plus j omega RC. So what I did here was, like, when you see resistors in parallel like this in this notation, like this right here, that's like the equation you use, right? So now we know that no matter what we have, whether it be a resistor, a capacitor, inductor, we're always going to be able to treat the impedances equally, like that. And that's what makes phasor analysis so magical, is that we can find the net impedance and stuff like this with without differential equations, just in terms of like complex numbers. Okay, Next part, part J, impedance of an inductor L and a capacitor C in parallel. Let's get another circuit going. Okay, here's our inductor. Same equation. So we can have L and in parallel with C. And what that comes out to is 1 over, oh wait, no, that's right, my bad. 1 over j omega c, which is equal to 1 over this. You'll notice that j omega basically always come in a package. So, sorry, missed an L here. But yeah, we're basically gonna always see these two together, and eventually, like a simplification we make a lot of the time is instead of writing j omega, we can just replace this with s, since yeah, it just means like the same thing. But of course both work. All right, so that's that part. Now let's move on to problem 3. Oh, this one's kind of a mouthful. Phasors through impedance. I guess I'll give you a second to read this first if you want to just, yeah, like pause it here or something like that. But yeah, let's get going. Yeah. You had a piece of paper? Okay. So first of all, wait, let me explain what the purpose of this is actually. So this is kind of explaining the purpose of phasors. You know, honestly, it would have been nice if this came earlier, but it's all good, no problem. First, we talk about how IV relationships are a little bit weird. Yeah, with standard analysis with differential equations and stuff, if you imagine like KVLing everything, if you have a bunch of like crazy resistors, capacitors, inductors in series parallel, like it's like impossible, right? So again, we make our little simplification with phasors and treat everything as like I like to think of it as an impeder almost, which is kind of like a resistor, but not all resistors, right? Okay. So this is our governing equation for phasors, right here. And it mentions we use these phasors, we use these phasors to create an extension of Ohm's law and capacitors and inductors. Yeah, so this looks a lot like Ohm's law, right? Like we've seen before, Ohm's law is just equal to V equals IR. And really, you can think of impedance Z as just kind of like a phasor R, okay, like a complex R. Yeah, so now we're gonna derive those equations earlier for inductors and capacitors. Remember, we had the inductance of a capacitor was equal to 1 over j omega c, and the inductance of an inductor is equal to j omega L. And yeah, I guess let's get started. So part A, let me get this pasted over. How do you do this? That's not how you do that. Okay, so this is part A. What we can do for this part is first look at what we're trying to find, I of t in the form of this. And remember how we defined the phasors, right? If you look at this. So let's go back to our definition of a phasor. They also give it to us here. So let's use these definitions. So first off, very important to do is write down this capacitor equation because it helps us basically solve everything. Well, not basically solve everything, but it helps us to derive the equation that we want to use, which is for I. We can't do it without this equation. So first, what we need to do is find I equals something, right? And we know that I is defined as the change in current or the change in time. So what we can do is we can take this equation and we go dq dt is equal to I is equal to change with respect to time of CV. And with capacitors, right, capacitance is a set constant. We don't really change that, which is just good. So this is going to be equal to C times dV dt, right? Okay, so that's our equation, I equals C dV dt. So let's take our voltage. We have V of t is going to be equal to V0 cosine this. What we can do I'll just use this equation right here and plug it. Oh, that's my bad. I forgot a omega. So this we just got from doing C dV dt, right? And you'll notice that like it doesn't look right at first because we have a cosine here. We're saying that the derivative of cosine is cosine, right? But what it turns out is that this is actually something that you can do because when you take the derivative of a sinusoid, specifically cosine, it's turning into negative sine, which is what the derivative is actually algebraically and geometrically, in every way, I guess, equivalent to simply a phase shift by pi over 2. So that's why this pi over 2 is here. Without it, we would have negative sine here, right? But convention is for signals to always be written in cosine. You might be wondering why cosine over sine, why that over negative sine or negative cosine. I don't know. Well, my professor just told me it's just what they do. Okay, whatever, who cares? Just go with it, I guess. Okay, so once we have this equation, we can further simplify. I'll just write out the algebra. And now we're going to use Euler's identity. If you remember from the very top, was, where is it? Here, this one. A and B. These are very, very important. Yeah, this is how we derive this stuff. Okay. Yeah, if it doesn't really make sense why these two equations are equivalent, meaning this one, and the one I'm about to write, please go back to the Euler's equation thing. It's trying to match that. Oops. Now, just a simplification. We use the phasors now. If you recall the definition for the phasor from earlier up on the page. Yeah, my bad. Holy. Wait, I'm sorry, y'all. I need a second. Oh. Okay, yeah, sorry about that. Back now. Yeah, so let's continue with our derivation here. First of all, just a quick notation thing that this worksheet likes to use that you might also see is when we see this, or for example this, what that simply means is the complex conjugate of that phasor. So, for example, if this is e to the ae to the j phi, if v phasor is equal to ae to the j phi, then that means that the complex conjugate is going to be equal to ae to the j negative j phi. See if you can work out why that is, like graphically with our representation of the complex plane earlier. Yeah, that's just something we're going to use. So with our simplification here, so I actually messed up. This is the complex conjugate of the phasor. Yeah, so let's keep chugging along. That's equal to omega c. Holy, okay. Okay, just to make sure every part of the simplification makes sense, you'll notice that this vector right here, complex vector, e to the j pi over 2, is simply equal to j. Because if we look at this, this is simply, if we write it in the form ae to the j phi, right? Phi is going to be equal to pi over 2, which is 90 degrees. And then a is going to be equal to 1. So by definition, a vector that is completely imaginary and positive in the imaginary direction with magnitude 1 is just going to be equal to j, just 1j, right? So that's why we can make that simplification right there. And the same with this negative j right here. If we look at our simplification from before, this is simply equal to negative j. And this, just j. And and then we end up with this little thing right here. So again, that that is the current as a function of time. Now, that's the first part, A right there. And now let's solve part B. Oops. All right, now try writing the expression V phasor equals I phasor times ZC. So for this part, we're assuming that we don't know the impedance of a capacitor ZC, and we're solving for it. That's like the point of the problem. So I guess I'll get to it. So something we know is that this thing over here is actually going to be equal to this. The representation of sinusoids as phasors, complex numbers, is not just a representation, but it's like the ratios are like accurate. So what we can do is we can simply take the V phasor and divide it by the A phasor by doing this. So let's get to it. Earlier on in the worksheet here, they solve for the V phasor here. I think it's pretty helpful to read this part of the worksheet for this part to make sense. Again, if there's any questions on your end, please text me or whatever. Not or whatever. Yeah, email me, text me. Always down to answer. Although I don't know about over break for you guys, but you know. Okay, so let's do this division now. We have, whoa, is that complete? Yes, okay. If we divide, we'll end up getting that the phasor E so this is V of t, okay. Which we can derive from Euler's formula from the beginning. And then if we divide it by I of t, which is this expression, we're going to get what we expect, which is 1 over j omega c. So this proves to us that z sub c is equal to 1 over j omega c. Okay, so that's that part. That's parts A and B right there. Now let's look at part C. And this is the same problem, but instead of a capacitor, we're now looking at an inductor. Actually, I'm just gonna do both these parts. The process is very similar. So what we're gonna do is basically find the time varying phasor, not the phasors, yes, the phasors, but the time varying signal as a function of the phasors, and then we're gonna divide them. And then see what expression we can get. Oh, and also earlier, right, so again, the governing equation is going to be V phasor is going to be equal to I phasor times Z. And that's what we use to calculate Z. So that's why we did this, right? Just a refresher there. Okay, for an inductor now. Let's write the relevant equation for an inductor, which is L equals, not what I was trying to write. Oops. And if we apply that to our signal here, we're going to get a similar expression, although not identical, right? Because it's an inductor now. Oh, by the way, yeah, this is the identity we're using. that I mentioned before. Maybe should have came a bit earlier in the worksheet, but no problem. Yeah, so if we follow a similar process, I guess maybe I should leave this one as an exercise. We will end up getting that you could check your answer against this. It's going to be a negative there. And then from this, we're going to get that Z sub L is going to be equal to J omega L. So again, that's deriving the impedance of an inductor. Okay, show that the impedance of a resistor ZR equals R is the last part of the worksheet. This one's really weird. But yeah, intuitively, you can see it by, I guess, visualizing how a circuit works in that the resistance, which is literally defined as V over I in Ohm's law, is really not dependent on anything except the resistance. But let's get into a mathematical proof of this thing. Which is pretty redundant if you ask me, but you know, yeah, what you gonna do, I guess. So again, our signal here. What we can know about the current is through Ohm's law that it's going to be the voltage divided by R. And then if we would just want to Z, we can divide the two. And we don't really need phasors for this. It's just going to be equal to R. Yeah, so that's that. This part of the course is kind of a big jump, honestly. For me, at least, I felt that like DC sources and like resistors and capacitors in series were somewhat like visualizable, if that's the word for it. I don't know. But once it gets into like the complex numbers, I feel like it's a bit abstract and definitely like harder to see. So this definitely took me the longest time to understand. So, I mean, again, like, please don't hesitate to ask me questions about this thing. My philosophy on this stuff has always been that intuition is the most important thing. Remembering equations will only get you so far, right? And knowing how this stuff actually works and doing stuff like the sanity checks for impedances, like I mentioned earlier, is always going to be very important. So yeah, I guess main takeaways for this would be whenever you have an AC source with, well, we're only considering sinusoidal waves here. What you can do is you can treat all resistors, inductors, and capacitors as like circuit elements with complex, meaning real and imaginary impedances. And then once you have those values, you can kind of treat them all as resistors in series in DC, except instead of real number resistances. And yeah, instead of that, we just have complex impedances. Yeah, in the following weeks, it's going to be a lot of this, going to be a lot of calculating the equivalent impedance of some like systems, but you can just treat it as resistors and in series and parallel, and that's pretty much all there is to it for calculating the resistance. And then you'll get into some more complicated, like seeing the output of some function, the output of some circuit due to some voltage source over a variety of frequencies, over a variety of amplitudes, like a bunch of cool stuff like this. Yeah, pardon my stumbling, it's kind of late. But yeah, that's all for today. Again, that's my number. Ask me about the worksheet, ask me about the homework. I know it's due tomorrow. Again, I'm sorry for not showing up on short notice, but I guess I'll try to do better next time. All right, have a nice break, you guys. I mean, I know I can't wait for this thing. All right, see y'all.